Hi everyone, my name is Krishna and today I'll be presenting our work on private ad modeling with DP-SGD. So this is a work in collaboration with many other Googlers. So quickly the agenda of this talk is I'll first go through introduction, then I'll briefly discuss hyperparameter tuning of DP-SGD, then title privacy accounting, and efficient implementation of DP-SGD in practice, and some results, and then Q&A. So let's get started. So uh, in DP-SGD training, the main difference compared to non-private training is that during the back propagation, before computing the average gradient, we need to compute, for example, gradient L2 norms and clip the per example vector as per a predefined L2 norm. So this is to reduce sensitivity. Once the per example gradient vectors are clipped, they're averaged, and then we add noise to this average gradient based on a predefined epsilon or privacy budget. I use privacy budget and epsilon interchangeably in this talk. So higher privacy budget, which is higher epsilon, indicates lower noise. Lower privacy budget, low epsilon, indicates higher noise. This noised and averaged gradient is passed on to the optimizer. So it was considered that trivially or naively implementing DP-SGD could lead to significant utility losses. Utility here is accuracy losses in ads models because they present few challenges here. So ad techs use ads models to decide placement of ads on websites and apps. Popular model is the PCTR model, which gives out a probability that shown an ad to a user will the user click or not. So it's probability of click for the advertisement. So it is click through rate. And we have a publicly data set from Criteo. We use this to conduct our analysis in this work. So it is a binary classification problem, and the utility metric we use is the 1 minus AUC loss. So ads models generally it can be very large. It runs into many billions of parameters. They have large embedding layers. The data for ads tasks is sparse. It has large categorical features which are sparse, and there's class imbalance coming from that. The probability, for example, in the CTR problem, the probability of click is much lower than probability that it is not clicked. So these leads to challenges because this leads to sparse gradients, and adding noise during DP-SGD training is thought to destroy the signal during training. So it was considered that unless we use very high privacy budgets, it's almost hard to train ads models with DP-SGD. In this work, we show a recipe for training ads models with strong trade-offs. Then we show a simple method to tune the hyperparameters. We use a new computationally efficient method to get tighter estimates for privacy accounting, and we implement DP-SGD in practice and realize low overheads. So first, I'll go through the hyperparameter tuning. During non-private training, so the more hyperparameters for these models are extensively tuned. So in this plot, the blue line indicates the best hyperparameters from non-private tuning used during DP-SGD training. We can notice that it doesn't perform very well in the private DP-SGD training. So there are other optimizers and parameters and learning rates which actually perform much better. Another thing to notice is that on the best hyperparameters also change based on the epsilon or privacy budget. So the best optimizer, learning rate, and other parameter combination on the right side, which is at a higher epsilon of 10, is very different from the best combination on the leftmost side, where epsilon is 0.1 and lower. So in this, so during our implementation, we actually first tune the batch size and L2 clip norm. So generally, bigger batch size tends to add less noise, for example. So noise is added once per batch after averaging the gradient, and bigger batches add less noise, for example. And on the plot top left in this slide, you can see that x-axis is batch size and y-axis is the Gaussian noise standard deviation added, for example. And as we increase the batch size, the noise, for example, decreases. However, this is during when we fix the number of epochs during training. However, in practice, like as we increase the batch size, models take longer epochs to converge. So instead of fixing the epochs, we fix the number of steps and repeat the same experiments. Here we see that benefits of increasing batch size on noise, for example, actually plateau after reaching high batch sizes. So higher batch sizes help. So what during our implementation, we first sweep batch sizes while fixing other parameters like noise and clipping, or with no noise, no clipping for one epoch, can find the best batch size. So one way is to find the batch size where the AUC loss has been increasing gradually and then it increases suddenly. So you can choose a transition point as one good option. So next is the clip norm. So clip norm inherently provides a bias variance trade-off. So if we increase the clip norm, the noise added to the average gradient is proportional to it. So it increases the noise standard deviation. However, it also, if we reduce the clip norm, then it actually cuts down the signal, as you can see in the graph below. So we can, after fixing the batch size, we can tune the clip norm to actually find what is just about right clip norm for our ads problem. Another hyperparameter that can be tuned is the micro batching. So as we discussed during DP-SGD training, need to compute, for example, gradient L2 norms and clip the per example gradients. However, clipping per example adds huge overheads. So a relaxed version of this is, instead of clipping per example, you can clip for a micro batch of examples. Say we have a batch size of 1,000. Instead of clipping for 1,000 examples, you can choose a micro batch size of 100, average the gradients for that micro batch, clip once for that micro batch. So instead of, now we have 10 micro batches, we clip so instead of clipping for 1,000 examples. So what we noticed is that small micro batches can actually improve utility, and ideally we would have thought micro batch size of 1 would be best, but in some small increase in small micro batches help. And this could be because when we average the micro batches, the effective norm of the average gradient is smaller, so the clip norm actually doesn't cut as much signal. So I think so. Yeah, in the plot below, we actually show that if we can optimize, if we can tune both clip norm and micro batching together, it actually gives better utility than clipping any one of them individually. Both of them have help with bias reductions in different ways. So next is that I'll talk briefly about how we achieve tighter estimates for budget. So till now, Rennie differential privacy accounting has been most widely used since the actual original DP-SGD paper. However, there are more latest advances which provide tighter estimates, and most of them are based on the notion of privacy loss distributions. So we use the connects dot algorithm, which is computationally efficient, to arrive at our noise parameters for a given epsilon. So what we notice is that using the PLD accounting with connect the dots algorithm generally gives us higher utility or AUC for the same privacy, and the benefits are greater at lower epsilons. So next, I'll briefly discuss how we realize an efficient implementation of it in practice. So naively implementing DP-SGD leads to huge inefficiencies, because we need to compute, for example, gradient, then its norm, and clip the norm before applying it to the parameters. This results in catastrophic slowdowns in training. So we don't need, for example, gradients. We actually just need the, for example, gradient norms. So there is a work by Ian Goodfellow where he provides a way to, and the pair work is cited in the slide, where it provides a way to efficiently compute, for example, gradient norms without actually materializing the gradients for fully connected layers. So we use this approach, since embedding layers can also be considered as fully connected layers with one hot encoded inputs. And since ads models mostly compose of embedding layers and fully connected layers, so we take this trick and apply it for the model. So what we do is we implement a two-pass algorithm. In the first pass, we compute the per example gradient norm at each layer, then get the per example gradient norm for each example for the model by aggregating it. In the second backprop, we use these per example gradient norms to clip the gradients before averaging. And after averaging, we apply the gradients to the parameters. So we observe that this generally results in about 20% slowdown than non-private model. However, it's much faster than the naive DP-SGD implementation. So in this plot, you can see that the naive implementation actually doesn't scale. It runs out of memory at it's very small batch sizes, whereas a fast DP-SGD implementation keeps up with the non-private baseline in both speed and batch size. So uh, with this implementation, we evaluated the PCTR model on the public criteria dataset, and we notice competitive losses even at high epsilons. So you can see at epsilon of 10, which is moderate epsilon, you can see 6.27% increase in AUC loss. And even if we go to very high epsilons, epsilon of 1 and epsilon of 0.5, still notice only we still notice competitive increase in losses. It's not catastrophically, so the model still performs well. There is no catastrophic increase in loss. So another comparison we did was we compared DP-SGD to another DP paradigm, which is label DP. So DP-SGD protects both the inputs and the output labels, privacy of both inputs and labels, whereas label DP protects the privacy of only the privacy of the predicted labels, the labels themselves. And we use randomized response mechanism to get label DP here. What we notice surprisingly is that at very high privacy budgets or at very high privacy regimes or very low epsilons, that is very low epsilon, DP-SGD outperforms label DP in AUC. So, and we think this is because randomized response at such low epsilons creates very random labels, which are very random and completely don't have much information, don't have any info on the specific example. So, but it was surprising that DP-SGD, which has better privacy guarantee, still outperforms it at low epsilons. So few takeaways before the end of this talk is, the optimal hyperparameters to get private model training right are different than non-private model training. Carefully implementing the DP-SGD at a system level can make it as fast as non-private training. Then competitive privacy utility trade-offs are possible on real-world SATS problems. Thank you. Now, yeah, have a good day.